Okay, I want us to make we solve this problem using Newton's law of motion. As you know, we'll state the second law, and the second law states that the rate of change of momentum of a body is directly proportional to the applied force. That is, mathematically, you can therefore say that the rate of change of momentum F is directly proportional to the rate of change of momentum over time. So it is the rate of change of momentum of a body which is directly proportional to the applied force. So now F is equal to mv minus mu over t. And if we factorize the mass, we are going to have m in brackets v minus u over t, right? And you know that the rate of change of velocity with time is acceleration. That is ma. So therefore, we have our net force is equal to ma. So that is what we are going to use in solving this problem on the board. First of all, let me rub off what we have. We've already laid the foundation that F net is equal to ma as a vector. So let's rub off the board. So I want us to make some assumptions. The first assumption we're going to make is that this m2 is greater than m1. So we have been able to make the assumption that m2 is greater than m1. So invariably we are saying that this body will pull this body forward. So the acceleration will be tending forward, while the acceleration here will be tending downwards. So we've been able to show how the acceleration is moving. Now, another thing that we're going to place on this diagram is the gravitational force as well as the frictional force. Now, on the second body, the gravitational force is tending downwards. So the gravitational force Fg, and we know that Fg is equal to mg, now which is mg. Another thing we are going to note here is that our frictional force is always acting between the body and the wall. So the frictional force is acting here. The frictional force, which is equal to normal reaction over times the coefficient of static friction. So let's continue with the first body. In the first body, consider the first body. Consider the first body, which is like this, and we know that the tension is here. The tension. So tension is always acting on the string, and since it is one string holding the first body and the second body, the tension will be the same. Okay, now let's go. The tension is here. The tension is here, while the frictional force is acting backward. So because the body is moving, acceleration is tending this way. It means that tension is greater than the frictional force. So then we apply our F net. F net is equal to ma. What's the net force here? It is tension minus the frictional force is equal to m1 times acceleration. So therefore, we're going to make our tension the subject of the formula. Tension is equal to m1a plus our frictional force. And you know that our frictional force is m1a plus the coefficient of static friction times the normal reaction. And normal reaction is mg, which is m1a plus coefficient of static friction, the mass m1 times the acceleration due to gravity. So this is our equation 1. Now let's consider equation 2 in this purpose. Now, I mean the second mass. And in the second mass, we have the tension acting upward and the gravitational force acting downward, Fg, which is equal to mg. So we apply the second law, which is Fg minus m minus the tension is equal to ma. So m2a. So we now have T is equal to Fg minus n2a. Therefore, T is equal to m2g minus m2a. So T is equal to m2 and g minus a. Here, we now equate equation 1 and 2. We know that this is equation 1. So if we equate equation 1, equate equation 1 and 2. So if we equate them, we are going to have m2g minus a is equal to m1a plus coefficient of static friction and its acceleration due to gravity. So we now have m1 over m2, which is equal to a, and which is equal to g minus a in bracket over a plus coefficient of static friction times acceleration due to gravity. So we have this. This is the formula to use in solving this problem. I hope we've been able to demystify this equation. In our next video, we'll give you a typical example in solving this problem. I hope to see you in our next class. Take care.